All right, so we kind of overall have finished up PLCs. All right, and relay logic. That's what we've been doing for like the last 3 weeks, I think it was. At least 2, if not 3 weeks. We've been working with PLCs and wiring them up and writing this very simple program and things like that. I think you all overall decided that you like the wonderful world of PLCs better than the wonderful world of just straight up relay. All right. I could be mistaken, but I think you all overall did. All right. And this is going to take us down a slightly different rabbit hole, all right, of inputs. When we've been dealing with inputs so far, all we've been dealing with are buttons. Buttons limit switches, right? And those are very discrete. They're on or they're off, all right? Now, is there any smarts to those things? No, right? You just put power in one side, you put signal out the other, and when you press the button, it physically metal-to-metal contact happens. Right? However, there are other options out there. Now, coming back to the world of PLCs for a minute, we had sourcing and syncing. All right, who can tell me the difference? You guys remember? No, I did talk about this. All right, one of them, the PLC is expecting a 24-volt signal, and the other one, the PLC is expecting a 0-volt signal. So the question is, which one is which? So on the screen, there's a left and a right. Is the one on the left sourcing, or is the one on the right sourcing or syncing? I don't care what you tell me. One on the right sourcing. I've got one vote for sourcing right. I'm gonna say syncing. Okay, Chris, you get to be the deciding factor. Which one's sourcing, which one's syncing? Which one's the first? Left or right? So I've got, you're saying sourcing is left. In the long run, you're saying sourcing is left, and you're saying sourcing is right. Left is the winner for sourcing. All right. And the reason being, the PLC is sourcing the voltage. It is supplying the voltage. All right. So if we look, the PLC on this left one, like how a minute ago, there we go, is connected to positive directly. There's nothing between positive and the PLC. So it has the common, remember how we had that common to ground for 0 volts? This one, for an input that's sourcing, we have to have the common would be positive. All right. And then the negative would be connected to the inputs. So how you guys wired thing up was in a syncing fashion. This is how you guys did it in class. And we had a positive going to whatever input device was, which went to the PLC, which then connected to the negative volts, and this was the COM location. All right, so that is what was going on. Now, you may be asking yourself, why the hell does this matter? We'll come back to that in a few minutes. Right. Now, again, everything that we've dealt with so far in this class has been boring old switches, right? Just a physical metal-on-metal contact happening somewhere inside the switch. Not that we actually see it, but that is what was happening. Right? However, that would be a mechanical device that you guys make. There are what are known as solid-state devices. So there are physically no moving parts. Right? And to accomplish this switching, they are using transistors. Right? A transistor is either an amplifier or a switch, depending on how you have it wired up. All right, so you could take a low voltage signal in and amplify it, or you can just say, hey, when this low voltage signal goes true, make this high voltage signal or high current signal go true, whatever the case is. All right, so there are different options there. So a transistor takes an amount of current on the input and amplifies it to the output. So really, it's always doing that. It's just a matter of whether you're using it as an amplifier to actually take a little current, make a bigger current, or you're just using it as a switch. Right? Most of the time for me, when I'm making my random circuits, my Arduinos, my microcontroller projects, I'm using it as a switch to take the 5-volt signal input to maybe a 12-volt signal, or the 3.3-volt signal into a 5-volt, or something like that. I'm just using it as a voltage switch. All right. But you can actually use it as an amplifier, which is really nice. All right, and as you can see up here, we do have an N-type and a P-type. All right, which we will look. Hopefully, I believe this video will talk about for us. So anyway, yeah. So transistors, they're great little devices for us. All right, they are solid state. There's no moving parts, which means there's nothing to wear out. All right. Now with the PLC and the buttons, every time you open that contact, there is a little bit of what's called spark. Even no matter how you have any button wired, and especially in the world of DC, every time you open that up, there's a small spark that's formed because there's current flowing, and that current wants to keep flowing. All right. So every time you open that, there's a little spark. That little spark erodes the metal away. Every time you open and close it, you are in theory wearing away your contacts. That is one of the big downsides of physical contacts happening. Yeah, with the solid state, the transistors, there's no physical contact opening or closing them. All right, so it's not as big of a problem. We're not burning out that contact. Right? Now, at the same point, hooking a button up to a PLC, we're not having as much current flow. All right, I haven't measured it, but if we actually would like look at the current flow of one of these contactors that we have on our boards, it might be half an amp. All right, if you look at it like to the PLC, it might be like 1/100 of an amp. So like the amount of wear and tear we're getting from turning a contactor on versus the PLC getting the signal, completely opposite ends of the spectrum. All right, so it's not something that we really need to worry about for burning out the contacts on an actual button or something. But those things do actually happen in the real if you have a relay logic or a high current flow on something. All right, so you do need to be careful about those types of things. And in fact, if you have too much current flowing through a button, you can actually weld those contacts together. Because they'll get so hot and so much sparks and whatnot that it'll actually physically melt the two contacts together. So when you let go of the button, it doesn't actually change. Or the relay close won't actually open those. So there can physically be those types of problems that occur. All right, so some basic switching as we kind of saw in the lovely video. All right, so here we've got our transistor. We got our relay up above it. So once we would close this switch, power would then be able to flow through this, which would then allow our different power to flow through this. All right. Anyone know why we have this diode here that says flywheel diode? Oh. If you notice, that diode is actually backwards. All right. The video very briefly hit it up, but basically, this side of the diode with the little line, that's the negative side. All right, so that would be the 0 volt side. You notice that is pointing towards VCC, so that's our positive voltage. So that diode is actually backwards. So on normal conditions, power would flow through and hit this and stop, which is good because if power flowed through that and didn't stop, it would come all the way through down to 0 volts and be a dead short, or basically a dead short. All right, so the whole purpose of that is to allow the current to have a place to go. Right? If you remember, I just told you guys that voltage wants to keep flowing. Right? When we open that switch up, it wants to keep flowing through that air gap. Like, no, let me keep going. That's why if you guys have ever seen a Jacobs ladder, electron there, we have two wires positioned on a V, and an electric arc jumps at the bottom, and it flows to the top until the arc gets too big, and then it breaks. And normally that starts bending at the bottom and just keeps doing that because that's just how it works. The electricity wants to keep flowing. So the whole point of this flywheel diode here is that when this opens, that current wants to keep flowing. Well, this supplies a path for it to then circle back to itself. All right, so it allows that energy to dissipate, not just like a hard stop. And that hard stop is likely, it could damage your transistor if you didn't have that diode in there. So that diode is a very important thing in the long run to have around. All right. So that is a basic NPN switching circuit, and so this is basically what is wired inside your PLCs. All right, especially the ones we have. These are transistor based. They're looking for DC voltage. That's transistor, whatnot. Now, if we quick look at the next thing here, we have some standard diagrams, and this is why this is important for you. We are starting to get into the world of smart. I'm going to put smart in air quotes here. Smart sensors. Right? And by smart sensors, I mean these sensors don't rely on a physical contact to make something happen. Right? There's no actual limit switch being pressed by something. There's no button that you're interacting with. It's you putting the pallet and getting close to the sensor, not actually touching it, and that's what's triggering it. You know, there's an air gap there, which is really, really convenient for certain situations. All right, but here you can see that we've got two different types. So if we look up here, you notice the arrow is pointing in, and if we look down here, the arrow is pointing out. All right, So depending on how your system is wired, whether it's a syncing setup or a sourcing setup, you need to use an NPN or a PNP type smart, again, air quote, sensor. All right. So because of how we are wired, we are doing syncing setups, we would be needing to use NPN-based sensors. All right. So that is a very important thing to take into account when you are picking these smarter, per se, sensors out. All right. So here's a quick diagram of it being wired up. Nothing too crazy going on there. All right. And then here we can start to get to the real loveliness of this presentation. All right. These smart sensors. Oftentimes, we don't want to interact with something. We don't want to touch it, right? For a few reasons. One, touching things can be hard with sensors, right? You have to get that pallet in the perfect position to hit that limit. All right, but, if you have a pallet going past something on a conveyor belt, you have to make sure that pallet is moved over perfectly. Now, your limit switch may have a half-inch room of acceptance where it will, something can touch it and actually trigger it. All right, and if we would actually look at the limit switches that you guys had on your boards, you would notice if you touch them, they don't trigger when you bottom it out. They trigger early. So again, you have an extra half-inch of play or whatever. Now that expects then that every pallet is built exactly the same. All right. Now, if we're talking about traditional wood pallets here that forklifts and things like that are moving around, over time they get beat up, things get moved, yada yada yada. It's might not trigger at the right spot anymore. All right. Now, if you're talking about some sort of metal block that you're manufacturing, sliding down, hopefully that is manufactured the exact same every time. All right, so a limit switch may work for something that you've manufactured, that you're physically machined, because you're it's always going to be 2.5 inches. So as long as I do this and it slides across right next to this edge, this limit switch over here will touch it. Well, now you could also be marking that surface up slightly. If you painted it or something, that limit switch could nick that paint if you don't have something set up quite right. So that could also be something. Where these sensors that we're about to talk about, these photoelectric and ultrasonic, they do not physically require any touch of the system, which is wonderful. Now there's no actual touching. We don't have to be as precise with something. We don't have to get the positioning exact right. The sizes isn't quite right. It's fine, right? So there are all sorts of options like that. So up here on the screen, I am showing you mainly photoelectric, all right? Which means we are using light for this, all right? And as you can see, there are 3 different options, all right? So option 1, which would be this one on the far left, all right, that is a through beam. Right. So here you can see we've got our emitter, this cone. And then on the other side, we have our receiver. So if this was our conveyor belt going, that was horrible. Now if our conveyor belt was going this way, this target would come down that conveyor belt, would get between the emitter and the receiver, and the PLC could then notice, hey, there's no light hitting my receiver anymore. Or that signal has been trashed. So there's something physically in the way. It's just like you standing in front of light source when someone's trying to read something behind you. All right. So great option. Now, what's the downside to this? Anybody? Nothing. All right. So one downside here is you need to have a sensor and a transmitter on different sides of the conveyor belt, which means we have to have wiring go to both sides of the conveyor belt. All right, so that could be problematic, or could be an area of concern depending on how your system is set up. Not the end of the world in most situations, but depending on what you're doing, this could be an issue. This is going to probably be your most reliable setup, though, for sensing, because you are physically putting an item in between it. All right, so that is nice. Also, these are normally set up to be a normally closed sensor, just like your e-stop was. All right, not an issue. Remember, in the world of PLCs, you're like, oh, let me just change the symbol. It's perfectly fine. All right, doesn't matter whether a symbol is normally open or normally closed for PLCs. In the software, you can just invert the symbol, and you got the opposite behavior out of that sensor, which is great. But it is something that you have to think about when you're writing a program. You're going, I need the make contact, the normally open, or do I need the break contact, the normally closed? All right, so you do have to think about that. However, another Downside here is alignment. Right? You have to make sure that these things are lined up correctly. Right? We actually have. All right, we actually have on some of our trainers this exact sensor. So we have the sensors over here on this side and the emitters over here on this side. So we actually just put 24 volts to this. There's a little LED inside that. So I can take that cover off so you can see it. There we go. You can see our little LED in there. And on the other side, we have the receiver, which actually looks just a lot like an LED. Oh, this one doesn't. It actually does look like a little receiver of some sort. But it's great. Alignment, though, can be a royal pain in the butt. All right, it's been very amusing for me with these because they will be off by a few millimeters, like left or right, sometimes depending on the system that we're using, and they won't work. All right, I haven't done it to this one, but some of our other trainers, I actually have physically rebuilt it. I'm like, yeah, this little 2-block down here is too big, so I need to move the sensor up one whole block width. And then that solves my problem of alignment because the light is just bright, a little extra bright that it allows it to work well enough. So it's kind of very interesting to me to see that and be like, it's got to be that specific, that close that it's that for it to work. So kind of annoying in that aspect. And I'm sure the industrial ones might be a little bit better, but they're not going to be a lot better because you don't want false positives. You don't want to be like, oh yeah, there's the light in the room is on. That's going to trip the sensor. No, you want it to be tight enough and not have a lot of allowance for things being off alignment. So that would be a through beam. Also, depending on your environment, airborne particles could cause a problem here. All right. Fun side note, this is how a lot of smoke detectors work. They basically have a light on one side and a sensor on the other, and when smoke gets in between, it diffracts enough of that light that it says, hey, there's particles in the air. Doesn't necessarily have to be smoke. All right. So that could cause your smoke detector to go off. So for me, in my family room where I have a fireplace with that sensor, I've tripped that just opening the door to my fireplace. So I had to replace it, put a heat type one in. So once it's, 200 degrees or something like that, that's when my smoke detection in family room goes off instead of based on a particulate in the air. So, however, another benefit here, these can cover up to 25 meters of distance, or over 25 meters. So yeah, you could use them like this, where it's a little, 5-inch or 4-inch space between them, or you could get better ones that could cover up to over 25 meters. All right, great example of this, another one, garage door openers. Your garage door, if you have an electric, you have that stupid sensor right by the foot, so that way if someone walks through the garage while the door is closing, it stops and goes back up. That's what's going on there. There is a sensor on one side, a little laser basically on the other, shining through and tripping, and you got to make sure that sensor is good. All right. So, yeah, just a nice real-world example there for you. All right, the next one that we have here, number 2. I guess I should go ahead and clear all my lovely ratings off again. Number 2, which is the one here in the middle. This is called a retroreflective. This has a distance of up to 10 meters. All right. Anyone roughly know how many feet are in a meter? No, nobody? All right. There are roughly 3 feet per meter. All right. It's not quite exact, but for me, that is a close enough estimation. All right. If you really want to get particular, there are 2.54 centimeters per inch, and there's 100 centimeters per meter. So you could do 100 divided by 2.54, and that would get you to your number. But I'm not worried about that. I just say 3 feet is a meter. Basically, a meter and a yard are about the same. I believe a meter is a little bit under, but again, for my purposes, 3 feet's close. It's about 30 feet, so that's wider than this classroom still. We could have a retroreflective sensor. All right. The benefit here is, as you can see, what do we have going on? Both things are on the same side. All right. So that is a huge benefit for wiring and whatnot. It's like, okay, we just put the sensor and the receiver on the same side, and all is good. However, what's on the other side? Some sort of reflector. All right. So we still do have stuff on both sides of the system here. All right. We just don't have power to the one. So basically, you're like, let's shove a mirror at one side. We'll put the receiver and the transmitter right next to each other, so that way it will go out. as it shows you here. It goes out, hits it, bounces. So we're going to have a slight angle to those, and that will allow us to, detect this across the conveyor belt and back without having to run power to the other side and things like that. So that is very, very nice. One of the downside here is that highly reflective objects can trick the sensor. Right? If you're like, hey, let's use this to count mirrors, it ain't gonna work, because as the mirror comes in, it just replaces the reflector and it will just shine the light right back to the thing. So probably not gonna work. So you do want to be kind of careful about that when it comes to photoelectric, or for the object going down the conveyor is really what I meant to say. You need to be wary of what type of object you're trying to count. All right. And then our last object now, also this one, what state is this one? Normally open or normally closed? Got one vote for normally open. I got 2 more votes. This one was normally closed, we said. This retroreflective. Normally open or normally closed? Two for normally open. All right. Nope, normally closed. All right. The light is shining. It comes out, hits the reflector, and comes back when there's no object being detected. So that means it's normally sensing there is a signal, which would be normally closed. All right. Just like this one, when there's no object in the way, the light shines through and hits that beam, hits the receiver. All right. So our last option is a diffuse option. All right. So there is no reflector. As you can see here, the receiver is on the same side as the transmitter. All right. So what is this one doing? How is this one different than the retroreflective? Go ahead. Maybe. All right. The real way this one is different is the object itself is the reflector. All right. So this one, the transmitter, as you can see by this red beam, sends a signal out, and when there's no object there, the receiver's not getting anything. All right. And once that object comes in, enough of that light that it's sending out hits that object and gets reflected, and then the receiver sees enough of that reflected light that it's saying, hey, there's now an object there. All right. So it basically works exactly as the retroreflective, except for the object itself is the reflector. Now, this obviously does come with a problem where color and distance are important. All right. This might work at half an inch with black colors and 2 inches with silver colors. All right. In fact, Matt had this exact problem. He's working on the robot over there. We have just a normal old retroreflective sensor like this mounted to the robot, and we were trying to use it for color detection. So it's not meant for color detection. It's meant for just saying, is there an object there or not? But depending on the color of the object, if you're an inch away, the silver will reflect, the red will reflect, the black does not reflect enough light for that sensor to pick it up. All right? So it's that exact game. So you can somewhat play material or color choice with it. Not really, but kind of. All right. So just kind of interesting in that aspect. So, but this one is normally open because, again, the signal is not true until the object is reflecting it. All right. So those are all photoelectric. Now, I did say we're talking photoelectric here, and I did misspeak. Photoelectric is using light. All right. What's ultrasonic using? Sound. All right. So all 3 of these work with light or sound. All right. There is not really a difference between them. All right. Obviously, there are probably benefits to both depending on the situation you're in, so you do need to be aware of that. But for the most part, it will work with either. All right. Now, something we haven't talked about yet is inductive and capacitive. All right. So photoelectric, ultrasonic, we've hit those up. We'll come back to those in a well, actually, let's start with this. So photoelectric, our sensing range is from less than 1 millimeter, all right, to greater than 25 meters. All right, remember, roughly 3 feet per meter, so over 75 feet you could use this for. All right, it's fine for small or large part detection, and you can do plastic, paper, metal, basically anything. As long as you can put it between, depending on the sensor type, right? If it's a through beam, okay, anything that will block the light. So a piece of glass, you're not going to detect probably with a through beam light. However, a through beam ultrasonic would work. All right, so you got to just have to be kind of careful there. For the ultrasonic, it says less than 30 millimeters, so that's about an inch. There's 25.4 millimeters per inch to greater than 2.5 meters. All right, and this one will do cellophane, thin plastic. All right, foam, glass, liquid, powder. All right. And then at the top, so inductive and capacitive. Inductive, all right, things that allow electricity basically to flow. That would be inductive, all right. So iron, steel, aluminum, copper, ferrous metals are inductive, all right. And these capacitive or inductive non-contact sensor is really what this is. All right, so this is saying less than 4 millimeters to greater to 40 millimeters. All right, so again, like about an inch to, about 10 or 20 inches, depending sensor. All right, and we're able to detect metal things. So a fork or something like that would be fine, but if you put a plastic fork in there, it wouldn't detect it. All right, if you need to detect that plastic force, that's when you need to go to that capacitive sensor. So that'd be non-ferrous materials like liquids, woods, granules, plastics, and glass. Can you still detect metal? Yes, you can still detect metal with a capacitive. All right. But if you can't detect plastic with an inductive, right? And this was that blue device on your boards that you guys are dealing with. I said we weren't going to touch. It's that blue 3D printed platform with the little green nib on top. That is what one of that is. I don't remember if it's inductive or capacitive. I could make you guys wire it up and test it. We'll find out. Maybe we will do that in a few minutes, just for some funsies here. But anyway. Yeah, so these are great because they're non-contact. All right, a lot of these will have a little screw terminal on the back, which will actually adjust the range. All right, so you can actually say, I want it to be a little closer range, or I want to accept things from farther away. So you can actually adjust the sensing field, which is very convenient. Oftentimes, like 3D printers will use these for their Z height. All right, if you don't want to use a limit switch, you could use this, and it will. Again, you can fine tune it to say, yep, that's how far away from the bed I want it to be. We actually have at least one of these printers like this in the other lab. And someone donated it to us because they couldn't get the Z height to work correctly. And I was like, okay. And I looked at it and I'm like, we just need to adjust this little screw here. And I adjusted it and tried and adjusted and tried and got it to work perfectly. I'm like, you want it back? They're like, no, you keep it. I was like, okay, like nothing wrong with the printer. They just had to adjust that little screw to get it to home right. So that was kind of funny. But anyway, so that is another technology we have here. Okay. Now here's the real fun thing. Coming out of a lot of these sensors, you will see these colors of wires. All right, red, green, yellow, brown, blue, and black. All right, so I want you guys to take a moment and figure out of these color schemes, which wires do you think would represent positive, which wires do you think would represent negative, and which wires do you think would represent the signals? Right. So, of these, you're going to have a positive, negative, and a signal. All right. So coming out the back of that, you've got these 3 wires. It's like, okay, now which one's which? That is the question that I want you to answer. So there's 6 colors here. These are 6 colors that you would see coming out of these sensors. So say you're like, oh, I think green is the negative. You should have 2 for each. So go ahead, take a minute, and figure out which one you think is which. All right, time is up. So, red, what do you guys think? Oh, let me go ahead and erase this green here. I don't know if that was correct, so we'll just go red. Green. Do you think green's also positive? Yellow. Brown. Chris is just shaking his head. He's like, I was too distracted. Blue. Black. Do we all agree with these numbers? All right. So the first thing I didn't tell you guys, which is causing problems, but that's okay, is these three were grouped, and these three were grouped. Ha ha ha! Gotcha. All right. Anyway, so the red or brown, that would be your positive. All right. Your blue or green would be your negative, and your yellow or black would be your signal. Yeah. I don't even ask. I agree 100% with you guys. I think it's wrong, but that is like the standard color codes that you will see coming out of these sensors. I mean, you guys had one right for each category. That was good. All right. So red, blue, and yellow. So yeah, not too bad there. But anyway, so looking at the actual proximity sensor here. All right. So here we've got it. You can see it is this device that we get screwed onto a surface. We've got, this is actually the sensing area here. And then if we look at the back, you've got some more screws to secure it, and then you got the wire coming out. And as you can see here, we got brown, black, and blue. Hope you guys can't see. There you go. All right, so as I said, kind of a weird order scheme here. All right, so I guess what we're going to do here, all right, since we got some time left today, is I want you guys to research this. I'm trying to get light there so we can actually read it. Get in focus. There we go. So here is the sensor information. You guys ready to write this down or type it on your phone? All right, let me just pause the video here. All right, so if we look at this sensor, if we look at the data sheet for it, all right, which is what I have up on the screen. Hopefully you all able to find that. We are doing the first one here, the 3RG4022OGB33-PF. All right, which does tell us that it is a normally open sensor. All right, so when there is nothing detected, there is closed, or the signal is open. All right. It does tell us for our size that we are using an M12. What does M12 mean? Really? Nobody? Take a wild guess. 12 what? Nope. Close. You're missing something in front of meter. 12 millimeter, mm. All right, so M12, metric 12, what they're telling us. All right. And so this is saying mounting is non-embeddable. All right. So here is that operating distance. So we can see we go up to 4 millimeters. All right. So that's what it's rated for. It is in theory effective from 3.6 to 4.4. All right. Notice that we've got little commas going on here instead of periods. All right. I think that's a metric thing or a European thing. All right. So just kind of something to be aware of. All right. So they're saying our standard target should be mild steel that is 12 by 12 by 1. So that's half an inch by half an inch, basically. All right. A repeated accuracy of 0.2 millimeters, you know, all sorts of fun things. Down here is some other important information for this sensor. So you can see that it is a 24-volt DC sensor. That is going to be important for us to know for wiring purposes. However, it will operate anywhere between 15 and 34. It always cracks me up. Like, that's quite the range. I mean, don't get me wrong, it's very handy to have that very high range. All right. Our no load current of 17 milliamps on 24 volts or 30 milliamps at 34. So if you cranked it all the way up to that 34 volt range, I don't know why you would, but it would. All right. Our output is a 3-wire system. Now, why do you think that's important? A 3-wire system. Go ahead. Okay. Kind of. That would be the reason for this voltage drop right below here, at 2.5 volts. All right. The reason 3-wire is important is because there are actually these smart sensors that are 2-wire. All right. They're called Vampire. So when they are no load, they allow a little, like they're always using a little bit of power. So they're actually sending the like PLC would detect a very low voltage. Like, hey, there's something being, using power here. All right. But then once that does detect it, the voltage goes up, or the current, or opposite, it goes down a lot, type of thing. All right. So there is actually like a switch. You can actually use just 2 wires to have one of these proximity sensors. All right. This telling us 3, which means we have positive, negative, and signal. Right. But it could actually be a 2-wire type of system. So that's interesting there to me. Short circuit strength is built in, so that is great to know that if you short circuit this thing, it shouldn't be destroying it. All right. Overload withstand capability is built in again, so that is nice. Frequency that this can happen, again, 800 hertz. Woo, that is quick speeds there. All right, and in theory, I guess time delay before availability is 40 milliseconds. I don't know if that's like boot up, like you plug it in and it takes 40 milliseconds before we'll start outputting a signal. That's my guess there. All right, we've got temperature ranges here, nothing too crazy there. Reverse voltage protection built in. That's great for you guys, right? We're going to wire it backwards. You guys wouldn't do that to me, would you? Never. Yeah, I know. All right. Basically, everything's built into this, which is great. There is a little LED indicator, which is nice. Right, and that's about it. So, anyway, that's kind of just looking at data sheets. Like, okay, you got one of these sensors, and you're like, your boss is like, hey, that burned out, go find a new one and order it. You're like, okay. And then you'll find it, and you're like, oh crap, it's discontinued. I can't buy that exact same sensor anymore. Well, this spec sheet gives you enough information to say, okay, I need a 12 millimeter diameter, hole, or technically maybe you could get away with a little smaller if you put some like washers or something on it. And it's like, okay, I need 24 volts. I need it normally open, yada yada yada. What would happen if you put it normally closed in? All of your logic in your PLC would be backwards. So you would then have to go through and invert all of your logic. Not the end of the world, but something you just kind of have to keep in the back of your mind. Right? So what we're going to do is a quick little app. Is we're going to wire one of these up, and you're going to put a voltmeter to it so we can actually see it outputting power or not. All right, so that is what we're going to go do. And if you want to take yours off too, Dylan, just unscrew it. By all means, please do. That way you can actually see your wire colors and things. That might make your life a little bit easier.